Virtual Reality Laboratory is the highlight of the Chicago Museum of Science and Industry's new exhibit, Imaging the Tools of Science. Throughout the exhibit are a number of stations that illustrate the many different applications of the digital processing loop: acquisition, processing, and display. The immersive station in the VR lab consists of a boom-mounted display providing both stereo images and spatially located sound. In addition to the user's interactions with the rich texture-mapped environment, 2 Macintosh stations allow additional guests to trigger events in the virtual world. For example, turning on the lights or calling the cops. The SGI 4D440 reality engine is a computational image for the SIGGRAPH. Here, 2 visitors are digitizing their faces, which then appear in the virtual world. There are 4 sections to the virtual world. First is the virtual model of the museum space itself. Then 3 additional sections are representative of the image processing loop: acquisition, processing, display. Users guided through this experience as if they were water skiing behind an invisible boat, free to look in any direction, but constantly being pulled along. The user does have local control over their position, looking toward an object and moving closer to it. In addition, there are forks in the river, and the user may take a different path depending on where they were looking as they reach a fork. This method of navigation allows the viewer to have control while also being guided.
So let's do a walk cycle. Actually, what we've been doing here is showing how quickly we could do a human walk cycle. There are a couple of little animations that we can go through quickly to show you how fast you can set something up. So let's do that. Let's do the walk cycle. Let's put a leg forward. Let's put the right leg forward for a first step. Put the left leg backwards. Again, be careful of these wires back here. The body normally twists in the direction that you're going to take a step in. Let's move the arms counter real fast and straighten the head out so that it's pointing in the direction that you want this guy to be walking in. You don't want his head bobbing back and forth as he's taking steps. You can go back and move the camera around and check it out and make sure that he's in the position that you want. And come down to the timeline. And I have the timeline set here for 21 frames. So I'm going to save a keyframe at the beginning. And I'll go to the last frame because we're going to ultimately want to loop this and save a keyframe here at 21. So I have 2 keyframes on either end of the timeline. Now let's go to frame 6, and I want to start walking this person. So the leg that's extended out in front, we want to straighten that leg out and have it straight down. The other leg is going to start coming forward, right? The knee will be in front of the body angle, main body angle, but the heel will still be behind it. You'll have that type of an angle. Grab both hands at this point and just pull them down. You want them both straight at their side. And you can talk about how you've just taken almost a dozen joints and quickly straighten all of those out. Straighten the body out, straighten the head out. You can go back here, move your guy around, check him out. He's lovely. Save a keyframe. Now, we can do the next keyframe, the next step, which would be have the opposite leg straight out. But in between those two final keyframes, keyframe 11 and 21, is going to be a keyframe that's going to be similar to this, but the legs are going to be switched. So now's the perfect time just to take that other leg and bend it in a similar position to the corresponding leg and just switch them. So now this one's straight down. Save this keyframe at frame 16. We'll save that. Now let's go back to frame 11, which would be the very middle of this walk cycle. And let's switch this step around. Before we had the right leg straight out. Now it'll be the left leg's turn. So I'll move that one out. We'll move this one back. We'll come back over here. I just hit a wire there. And move this. Straighten the head out. We've just done the middle keyframe. You know, we can go back in here. We could be a little bit more specific. Save that. And now we're done basically using the monkey. Benefits of taking motion capture and going directly into the animation system, our character animation system, Kinemation, we can also alter that information at this point. So I'll go in here and grab just the root of our body here and say that when you go through a walk cycle, when your leg is straight, the body tends to shift up. So let's do that. So I'm going to go to those 2 keyframes, keyframe 6 and 16, and holding the control key down, I just want to shift the body up a little bit and then shift over to 16 and do the same sort of thing. Save that again. And I have the similar keyframes at 1 and 21. I don't really want that because there'll be a little hit in the loop. So I'll go to my keyframe, my timeline right now, and I'll go from frame 21 and I'll shift it a frame down to frame 20. I'm in loop mode. When I hit play, there's our walk cycle. In a similar position. I can stop this and say, not only was I able to bring motion capture in, spline all of that information, I set it up in poses, I can alter those keyframes manually in Kinemation, but I can go back in there, open up a line of communication again, and I can alter some of these positions with the motion capture information. I can change and alter these keyframes, make sure I am in my skeleton mode again here, and save that keyframe. And that was just, so I've gone motion capture into Kinemation, I've changed keyframes, I've added keyframes, moving the root around, and I've gone back into motion capture again. So I've had this ability to go back and forth, back and forth, back and forth constantly. And this generally blows people away, especially when they can see how quickly you can do a realistic walk cycle like this, and just playing with it, where I can move the body around in all different directions like this, generally sells them on the idea. That's the basics of the monkey and kinemation.
I'm going to demonstrate a system that supports intuitive interaction for creative and cooperative work. The system is built on top of ATR's Virtual Space Teleconferencing System, and it gathers a group of people in a virtual environment, providing them with tools to perform this kind of work. As you can see, the computer understood my command and placed a tori, which is the entrance of a traditional Japanese shrine. I will show you how I can select different objects. Let me first take this object out of the way. As you can see, there is a green bounding box surrounding the chamber of this portable shrine, telling me that the computer understood what I said. As you can see, there is a laser coming out of my finger, and as it touches the different objects, there is a white bounding box surrounding them, telling me that they are on my pointing direction. Sono heya o Sono heya o右へ移動するあの屋根をここに持ってくるSo as you can see, it came right to my hand, and I can now very quite easily grab it and move it around. Ho, 立ち台にくっつける担ぎ棒を丸める and I can also 部屋を高くする and I have this completed for Omikoshi, which is a Japanese shrine.
This tape is an introduction to object associations, a method for simple and practical interactive manipulation of objects in a 3D virtual world with a 2D input device. Objects in a 3D world have 6 degrees of freedom. Even if you limit yourself to translation, you can control at most 2 of the 3 degrees of freedom with the mouse, so an object like this plant may float in space at some arbitrary distance from the user. Even if you could control the depth interactively, it would be hard to align furniture with the floor and walls, since you can't readily observe these alignments without changing your viewpoint. Now we turn on object associations. These are procedures that put some intelligence into objects, so that they know how to behave in natural and useful ways when dragged with the mouse. For example, one association called pseudogravity causes objects like this plant to sink down to a supporting surface. Note that natural and useful motion does not imply that we are constrained to physical realism. If we want to place lights or sprinkler heads at ceiling surfaces, we use an association called anti-gravity, which acts just like pseudogravity, except the object is aligned with the surface above it rather than the surface below. This behavior is very useful, even though it's not natural. Object associations are procedures that are bound to objects. They are called whenever the objects are moved in any way, and they control the precise placement and alignment of the objects at their destination position. The first job of an association is to disambiguate mouse motions in the view window into 3D motions in the virtual world. First, they choose an appropriate 2D surface for the object to move along. In the case of this cup under pseudogravity, that surface is the desktop. The mouse cursor ray is intersected with that surface, and the object is moved to the intersection point. This disambiguates the mouse motion into an appropriate motion of the object in 3D, so that the object may be dragged in an intuitive manner. But this simple relocation scheme, without pseudogravity association procedure, is not good enough if there are obstacles in the way, like for example this pile of books. The cup will slide through the books as if they weren't even there. For most application domains, this is not appropriate. The pseudogravity association will fine-tune the position of the object after it's dragged, such that its resting position is a valid one. When we reactivate pseudogravity for the cup, it will slide up on top and over the books rather than through them, which is a more desirable behavior for the cup. This whiteboard uses a different association, which we call the on-wall association. On-wall looks for nearby vertical surfaces and aligns the object's back with the closest vertical surface. This means the user is freed from explicitly turning the picture. They can simply drag it to the desired point on the wall, and the association takes care of the orientation and fine placement. The implementation of these mechanisms involves ambiguous trade-offs. Often it's not clear what should happen, and we had to make some assumptions about what other users might consider reasonable behavior. For example, what should happen if you slide a coffee cup off the supporting surface of a desk? Here we decide that the pseudogravity association procedure should move the cup straight down onto the next supporting surface, i.e. the floor. If you've made a mistake, you can move the mouse back to an earlier position and the cup will jump back up onto the table. If we want to move the cup underneath the desk, we move it off the desk surface so it sinks to the floor. We let go of the cup for a moment and grab it again by clicking on it again. This establishes a new association of the cup with the floor. Pseudogravity now moves the cup primarily along the floor, and we can easily move it under the desk as long as we can see it. In deciding when the user wants to lift an object up as opposed to dropping it down, we use the visibility of the cup's resting position as the most important cue. If we move the cup into interference with any part of the desk, or move it so that the sight ray through the cursor gets intercepted by the desk, while the cup is under the shadow of the desk, we take it as a strong hint that the user wants to move the cup back up onto the desk. Pseudogravity causes objects like the cup to sit nicely on valid supports, but what happens if we move the support? The association mechanism remembers which supports the object aligned itself with, such as the books the cup was resting on. When the supporting surfaces are moved, the system will automatically group the object with its support so that they move as a single unit. Some objects have behaviors that are combinations of other simpler behaviors, represented by combinations of associations we've already created. For example, objects like this bookcase maintain their back to a wall like pictures and sit on the floor like desks. They are assigned both pseudogravity and on-wall associations, and they naturally move in a way that satisfies both constraints. It is thus easy to align a row of bookshelves or file cabinets along a wall. You can see how easy it is to make realistic-looking placements in a 3D virtual world.
Cambrold is a system for implementing intelligent camera control. Camera tasks are encapsulated into well-defined units called camera modules. These camera modules can be programmed and sequenced, and thus be used as the underlying framework for controlling the camera in a variety of graphical environments. This video demonstrates two examples, a virtual football system and a conversation filming agent. This is a play from the virtual football system, recorded in real time on an SGI reality engine. Using the virtual football system, the user can create any desired play and use Cambrold to help visualize the play from any point of view. Here, the user is clicking on a number of preset camera locations, and the scene is shown from a corresponding viewpoint. Those locations are in fact the real positions used by television sports directors when filming professional football games. The user can also click on any player or players, and the view is constrained to keep those players in the frame. The user can also directly interact with the graphical depiction of the camera modules. By double-clicking on a controller icon, the user can create a new instance of a controller and name it. A particular behavior is chosen for that controller, which lets the user move the camera by clicking on the crosshairs. The camera is further constrained to always look directly at the ball. The user can then interactively move the camera around the field, while it is automatically constrained to look at the ball. One can study the situation and find the perfect position to understand the play before instructing Cambrold to take over and automatically perform a series of shots. In this case, following the quarterback, then switching to a ball's eye point of view, and finally switching to a view of the receiver catching the ball. This example shows a visual programming language where constraints can be dragged into camera modules. Modules can contain initial camera positions, different controllers, or multiple constraints. By dragging a single projection constraint into the camera module, a view is automatically found which projects a given object onto a specified screen position. This view is found via a constraint optimization technique. Additional projection constraints can be dragged into the same camera module, and Cambrold will attempt to satisfy all the constraints contained within the module at the same time. The same technique can be used to generate standard cinematic shots, for example, a medium close-up. This visualization shows how an over-the-shoulder shot can be achieved. 3 constraints have been dragged into this camera module. One actor is constrained to lie on the left side of the screen. The other actor is constrained to lie on the right side of the screen. In addition, the camera is constrained to look into the first actor's eyes as much as possible. The camera cannot achieve all 3 constraints at the same time, so it uses the best combination of these constraints to achieve its goals. In this series of shots, a conversation agent starts the camera outside of the room and then smoothly moves to an over-the-shoulder shot, found using the set of 3 constraints just described. The agent then switches to a corresponding over-the-shoulder shot to capture the reaction of the other actor. The agent continues to film the virtual conversation using a variety of different shots, all automatically found for each actor, including close-ups and extreme close-ups. The Cambrold system has also been successfully used for a number of different applications, including a walkthrough through a virtual museum, virtual surgery, a strategic mission planning system, and for film pre-visualization.
The goal of this project is to create an intuitive interface for painting on 3D surface meshes. Our approach uses the sensor of a Polyhemus space tracker as a paintbrush. Given a physical object, we create a mesh of its surface geometry. We paint the mesh by moving the Polyhemus sensor across the surface of the physical object and coloring corresponding locations on the mesh. We have implemented several different painting filters, including an overfilter which covers the previous color with a new color. This sequence shows the use of an alpha blending filter. Using a displacement brush, we can change the geometry of the mesh. Here we use the displacement brush to extrude bumps from the mesh surface. We have also implemented the ability to paint textures onto a mesh. For three-dimensional texture mapping, we use the position of the mesh vertex as an index into a texture map. Here we paint with a checkerboard texture. For two-dimensional texture mapping, we perform an orthogonal projection of each mesh point into the texture plane to create the mapping. We have implemented a separate interface for specifying the orientation of the texture plane in relation to the orientation of the mesh. Here, we have combined several brush effects in painting the bunny mesh. Using a Cyberware 3D laser range scanner, we can capture part of the geometry of an object. By scanning the object from multiple viewpoints and combining these scans using a zippering technique developed by Greg Turk and Mark Lavoie, we can produce a complete mesh for the object. Here we show Turk's program preparing to zipper together two scans of the bunny. Initially, we must register the Polhemus sensor to the mesh. We use an iterative method developed by Paul Bessel, which produces a shear-free transformation between the sensor coordinate system and the mesh coordinate system. Bessel's method requires us to collect many points along the surface of the object and perform an initial alignment of these points to the mesh. The advantage of this technique over others that use two-dimensional devices for input is that in our system it is always clear where the mesh will be painted. The physical object provides a force feedback guide telling us exactly which parts of the mesh our paintbrush will affect.
Volume sculpting is a modeling technique based on free-form interactive sculpting of a solid material. The 3D volumetric model is represented in a 3D raster of voxels, where each voxel stores local material properties such as color and texture. In this video, the process of volume sculpting a chair from a block of wood is shown in real time. Sculpting is done by moving 3D voxel-based tools within the model. A user first specifies on the projected image the region to be sculpted. Then, by adjusting the depth of the extrusion, the 3D tool volume is generated on the fly. The 3D tool volume is volume sampled to prevent object space aliasing. Note that since view-independent attributes such as texture are stored within each voxel, there is no additional processing needed for texture mapping. Then, a rectangular region is drawn to cut out the bottom portion of the chair. To achieve real-time interaction, a localized ray casting is employed for image updating. To create curvature at the back of the chair, a 2D curve is drawn and extruded to 3D to form the tool volume. Then the same tool volume is reflected vertically to generate a symmetrical cut. To provide more detail to the chair, slits are cut at the back of the chair. Again, by using the reflection capability, a symmetrical slit is cut. Next, the entire solid material needs to be rotated 90 degrees with respect to the y-axis, and the entire image needs to be regenerated. Nevertheless, the entire image can be rendered in a few seconds. A user then cuts out a rectangular region to form the legs of the chair. Finally, to see the resulting product, a high-resolution rendering is employed to generate a high-quality image. The chair seen here is 70 by 130 by 70 voxel resolution, and the image consists of 300 square pixels. In this animation, the table and chair were generated using volume sculpting. The scene is rendered using volumetric ray tracing to capture the global illumination effect. Note that there is not a single polygon in this animation. All models are voxel-based. In this animation, the sculpted windmill is placed on a volumetric fractal terrain. The simulated smoke is rendered using volume rendering. Again, there are no polygons in this animation.
This is a demonstration of the Tecate data exploration utility. Tecate provides access to various information sources or data spaces through the use of interactive virtual environments. The first Tecate example we show is a web browsing example. Here we show a 3D informational landscape. Icons on the landscape represent various URL sites. Here we zoom into an icon representing the San Diego Supercomputer Center. Tecate's object modeling language, AVL, allows the definition of both behaviors and state variables on objects. Here we've bound a behavior to display the URL information for an icon to a mouse pick event. We've also bound another mouse pick event on a different button to going over the network to open up the URL document itself. Here the document's been opened up and we see it represented as a pyramid. The fetch data, in this case HTML, is converted to AVL primitives. Here we see a page of text with the strings represented as 3D primitives. Active hyperlinks are shown, highlighted in blue. These are also Tecate objects with the same behaviors as the icons represented. Clicking with one button shows the URL. Clicking with another button opens up the actual document itself. Here we show later in a browsing session. By stacking 3D pyramids, we can show the path of relative links taken from a page. We can also attach other information sources to Tecate. Here we have a database of URL sites. By typing in a keyword, we can perform an SQL search to look for URL sites that match the keyword. Here we show supercomputer centers. And by changing our keyword to skiing, we'll show icons representing sites which are relevant to skiing. We also have the ability to directly embed AVL documents within websites. Here we show a series of icons that represent web documents, and by opening up one, we read in the AVL directly into the system. Because AVL allows the definition of behaviors, these objects come in as active objects, including interface. They're fully 3D, so we can rotate, and we can also apply behaviors, such as a behavior to spin the wheels. This allows us access to networked virtual environments. The next example we show is using this for an Earth Sciences visualization example. Tecate was developed for the Sequoia 2000 project. Our scientists wanted an easy way to access various information sources. Here we show a visual querying tool that's used as the front end to a database system. Pulling a bounding box allows us to set spatial constraints, calendar buttons temporal constraints, and hitting the Run Query button sends the actual SQL query to the database. The datasets returned within that spatial and temporal region are shown here as icons. Clicking on a button will show us the metadata representing the icon, here a regional climate model. And clicking a different button allows us to actually visualize the data. The first step in visualizing the data is to specify a task. The task statement represents how the user wants to participate in the visualization, the task operation, as well as the domains of interest they're interested in looking at. Here we specify that we want to search for temperature data. This task statement is sent to an expert system which writes a data flow program to represent the data. Here the regional climate data is shown as an isosurface of temperature values. The visualization comes in as an active 3D Tecate object, including interface widgets to change things. Here we have a widget to change the ISO value. Because of the ability to dynamically create user interfaces, Tecate can provide a very simple interface with just the relevant interface widgets. These two examples show a simple interactive 3D interface to a variety of data sources, such as the World Wide Web, database management systems, expert systems, and data flow engines. It is our hope that providing a simple interface to such a complex data environment will allow users to concentrate on their information instead of the process of gathering it.
What you are seeing is the tangle of vortices that comprise a turbulent spot in a fluid flowing downstream across a flat plate. The moving clouds in the distance indicate the free stream velocity. We explore this time-varying data set using an interactive graphic system called Tractor. The turbulent spot begins its development as a single horseshoe-shaped vortex. We would like to smooth out the animation by morphing vortex tubes across successive time steps, but that takes too much compute power. On the other hand, we can advect the geometry to match the flow. We can also advect the viewpoint, carrying it downstream along with the turbulent spot. This portion is being replayed at twice the real-time speed. The Tractor system provides a data probe for querying values along the vortex cores. You can display the vortices as polygon meshes, and you can decimate them to increase the frame rate. You can increase it further by displaying the vortex tubes as fat polylines, using a lighting model for large codimensions. The Tractor system proved its usefulness by helping to locate a particular flow feature, a rampant vortex head. This feature was first seen in a wind tunnel experiment where blue dye was injected into a flow. The dye marks an upright head and the bend at the center of a vortex. In a diagram from the Journal of Fluid Mechanics, this vortex head even tilts backwards. Here, an S-shaped head develops in a direct numerical simulation of the turbulent spot. How important are the shadows? How important are textures for an interactive 3D application? How useful is it to slave the eye point so that it follows the center of interest in a turbulent flow? How important is it for the vortices to slide downstream between the time steps? Well, when these facilities are disabled, we find that the 3D animation is less realistic and the user is more likely to become disoriented while examining the flow. Tractor has a homepage on the web that tells more about it. This link, for example, offers a list of all its known bugs.
In this video, we demonstrate a variety of techniques used for controlling the behaviors of real-time simulated human agents. Each agent has an underlying behavioral net which controls their behavior. The net is composed of three different types of nodes: perceptual, motor, and control. In this example, we're looking at one of the perceptual nodes, which is a proximity sensor. It can detect any kind of object within its shaded area. Changing various parameters of the sensor results in better motion. In this next scene, we see the operation of a walk motor node. This node controls the scheduling of steps to be taken by the agent. It integrates the output of perceptual and control nodes and blends them together and samples a potential space of where to place the foot for the next step. In the following example, we'll have several pedestrians walking through an urban setting, crossing the street, avoiding cars, other pedestrians, and respecting the traffic crossing signals. The agent in the upper left has been given the instruction to approach the crosswalk, wait for the signal to turn red, and then cross. The user has interactively positioned the vehicle in the middle of the crosswalk. The agent also has been instructed to avoid the car at all costs. The traffic light is green, so the pedestrian stops, waiting for it to turn red. Of course, our agents have perfect knowledge of the environment, even though they can't see the light from their perspective. One of our agents starts crossing the street, senses the car, and then will walk around. To improve interactive performance, we're only sampling steps, about 1 out of every 20 steps. The motion in the preceding scenes was generated with some very general but yet very slow motion generation algorithms. To make our agents useful for interactive 3D environments, we have to endow them with real-time motion execution. Here we're showing a system which can execute the motions of many agents simultaneously in near real time. Each agent is modeled with 3 levels of detail: a high-resolution body of about 4,000 polygons, a medium-resolution body at about 500, and a low-res body at about 120 polygons. Here, as we get closer, the higher level of detail pops in, the medium and the lower at the farther distance. Here I'm just showing each level of detail up close to the camera. This is the low resolution, the medium resolution, and the high. Once the behavioral controls for the pedestrians of the previous example are integrated with the real-time motion execution of these soldier agents, we will have a very general purpose system within which to experiment and build more and more sophisticated behaviors for our interactive human-like agents.
The position of the hand model in this kitchen environment is controlled by the user's hand. Notice that the hand model often penetrates the other objects in the environment. A better simulation might provide some visual feedback when the user's hand collides with these other objects. The lack of collision detection in this segment detracts from the realism of the simulation. We now use bounding boxes like these to detect collisions. The bounding boxes representing the user's real hand penetrate the faucet, but the virtual hand does not. The hand polyhedra turn red to indicate collisions, and they don't penetrate other objects. We consider a bounding box overlap to be a collision. We efficiently determine bounding box overlaps using a new dimension reduction approach, which we explain later. Notice that using bounding boxes for collision detection can be unrealistic. The hand is clearly not touching the chair. An object like this cone-shaped table cannot fit tightly into a bounding box at any orientation. Next, we show an exact collision detection algorithm proposed by Lin and Canny.
The hand is composed of multiple convex polytopes, each of which is tracked separately against the stationary polytope. Each white line connects a pair of closest features. A feature is a vertex, edge, or face, and it defines a Voronoi cone of closest points. We can track the closest features of two polytopes by performing a local walk. Due to coherence, we only traverse a few features each frame to find the new closest ones. The running time of this algorithm is nearly independent of the complexity of the polytopes. The tight-fitting, axis-aligned bounding box you see here is dynamically resized using a hill-climbing algorithm based on the properties of convex polytopes and the principle of coherence. We use these bounding boxes to pare down the potential number of collision tests. We project the bounding boxes onto the X, Y, and Z axes and sort them in 3 lists. If the projections overlap in the X, Y, and Z dimensions, we activate the exact collision detection algorithm. Each frame, we update the previously sorted lists by making a single sweep over them, pruning out the pairs of bounding boxes that don't overlap. Each polytope in the environment is now surrounded by a bounding box. We only trigger the exact collision detection algorithm now when 2 bounding boxes overlap. Because of coherence, our sorted lists of bounding boxes change very little from frame to frame, so we use a bubble sort or insertion sort to update these lists. Recall that without the bounding box hierarchy, we would have to make many more calls to the exact collision detection algorithm.
We return to the kitchen model and show collision detection to the accuracy of the polyhedral models and the tracker. Notice that the bounding box overlap check and Lin and Canny's exact collision detection algorithm run at interactive rates on a large data set. The collision response is more realistic now because the collision detection is more accurate. This environment, like most realistic environments, is fairly static. Hence, the sorting to detect bounding box overlaps is minimal. We've shown that interactive collision detection with simple response is feasible in large environments. This is another scene with hundreds of polyhedral objects. Notice that in our split screen, our collision detection and response is done in real time. This verifies our system can be used at interactive rates. In fact, the time for collision detection scales nearly linearly with the number of objects.
The real-time, multi-body simulation you see here shows hundreds of complex objects in a dense environment. The objects are placed in a 3-dimensional simulation volume where they bounce off the walls as well as each other. Unlike the walk-through environments, all the objects are moving simultaneously. As we increase the number of objects in the simulation, the number of possible interactions increases quadratically, but the frame time for our collision detection algorithm increases only linearly.